Okay, that's what boiling is. Okay. All right. Did you have your question?
No,
Okay.
answer.
So, by the way, so inside the sun, protons are colliding and combining and following making helium. And this guy, of course, weighs less than this guy by about 1%, and that missing mass is converted to energy. Okay. Now, of course, these guys, protons are positively charged and they repel each other. They don't want to come close together. Okay. To form the helium molecule, you have to come within 10 to the power of 15 meters, so then strong force can take over. Okay. So inside the sun, only the fastest protons fuse together. Okay. So inside the sun, protons in the tail have enough velocity to overcome the repulsive Coulomb force to undergo fusion. Water molecules in the tail of the distribution will escape from a pond. That's evaporation. All right, so we defined sort of, so this is the most probable velocity, this is the mean velocity, this is the root mean square velocity. So those are the three velocities. They're all roughly, equal. You can think of them as the average velocity. Okay, and that's what that table gave you, the RMS velocities. Okay, root mean square velocities. That table gave you these velocities. Okay. All right, now let's review something. So here's a object, here's a mass. To lift it, the force I have to apply is equal to the weight. Okay, and the work I do is the force times the distance, h. Okay, so mgh. So if I lift an object through a height h, that's how much work I've done. mgh. All right. Can a gas do work?
Yes.
Okay. Yeah, that's correct. So here's how a gas can do work. And so the hot gas in your car engine is doing work. It's okay. So how do I make the gas lift this weight? Let's say I heat the gas will expand and it'll lift this object up. Okay? So an expanding gas can do work. And it turns out that the amount of work it does, if it's doing it at a constant pressure, this is the amount of work the gas does. Okay? P, the pressure it's applying, times the increase in volume. To do work, what is it that you need? You need energy. If I want to do 100 joules of work, I need 100 joules of energy. Okay? So to do work, so remember that. All right, so you need energy to do work. Now, here's another thing you want to understand. This is a very useful tool. What we'll do is, here's the pressure of the gas, here's the volume of the gas. Okay? Okay, so let me do something to this gas. So, okay, I'm going to heat the gas, okay, and watch what will happen to the temperature and pressure. So I took the gas through a process. I heated it, and what happened?
Temperature and pressure.
Pressure increased, the volume was constant. See, that process that I showed you can be represented. There is the initial pressure, the volume was constant, and there is the final pressure. That process that I did is expressed by this diagram. Yep.
If it's a closed system, though, isn't it usually like a square? Or is that,
I'm sorry?
if it's a closed system, isn't it usually a square, or is that wrong? Like for the PV diagrams?
Oh, no, you're thinking of a cyclic process.
Okay.
Yep. So you saw that that process was expressed by this diagram. Anything you do to the gas, as long as it's the fixed number molecule, can be expressed like that on this diagram. So this is very useful. What is this process? I don't know what it is, but it's what are we doing? We are increasing the volume and pressure and so on. Okay. But any process like this, you can break it up into small continuous processes. Here, this is increasing the pressure, increasing the volume, pressure. Okay. Yeah. What was that process?
Like increased temperature and volume.
Yeah.
The pressure is the same.
Yeah, so we kept the pressure the same, so it was this process. Okay? That was a constant volume, constant pressure process. Okay? So the point is, I can do various things to the gas. The gas can go through various processes, and you can express that in this PV diagram. So this is a very useful tool. Okay? All right, why are we talking about this? Okay, now let's do the following. We're going to heat the gas. Okay, so I'm going to ask you, so PV equal to NKT. Okay. When the temperature is constant, these two guys are related, inversely related. Okay, so constant temperature processes, they're hyperbolas. Okay, so if you plot NKT over V, if this is constant, as volume increases, pressure decreases, and they're hyperbolas. So along these points, along this curve, the temperature is constant. Those are called isotherms. Okay, so think about this before you answer it. Now what we're going to do is we're going to increase the temperature of the gas. We're going to heat it. Okay. So I can heat the gas in various ways. Okay, I'm going to heat the gas. Let's say this is 300 degrees and this is 301 degree Kelvin. I'm going to go along this path, raise its temperature to 301. Or I'm going to go along this path and raise the temperature to 301. When you come to 301 degree Kelvin, the average kinetic energy of the molecules is the same. It doesn't matter whether you go along this path or that path. When you go to the final state, the average kinetic energy per molecule just depends on the temperature, right? So when I'm heating the gas, I've got to speed up all the molecules. I got to go from initial temperature to final temperature, so I have to increase the kinetic energy by the same amount. So is the heat added along this path the same as the heat added along this path? So you have to spend energy to speed up all the molecules. You sped up all the molecules the same amount along both paths. Now the question is, did you spend any money to do anything else? Okay. When would you spend money if the gas did work? Did the gas do any work along this path? No, the volume was constant. You didn't do any work. Did you do work along this path? Yes, you did. The gas expanded. So you had to add more heat in raising the temperature along this path than along this path. This is a constant pressure process. This is a constant volume process. So when you heated the gas along a constant pressure process, you had to add more heat. So, okay, so when you're adding heat to a gas at a constant pressure process, to raise its temperature by a certain amount, you have to add more heat. So this is the specific heat, molar specific heat for a gas at constant pressure. So this guy is greater than this guy. So the amount of heat you're adding at constant pressure is greater than the amount of heat added at constant volume. Okay, we didn't have this problem when we were dealing with solids and liquids. All we had to do was mc delta T. Okay, that was the specific heat. Okay, but when you're dealing with gases, since their volumes can change tremendously and work can be done, so we have to define two specific heats. And we define molar specific heats because it's easier to measure how many moles you have of a gas rather than the mass. Okay. So Cp is greater than Cv, and for ideal gases, you will learn Cp minus Cv equal to R. Okay. So that is a constant. Okay. So that's interesting. That's the same whether you are using methane, nitrogen, oxygen. It doesn't matter what gas it is. Okay. All right. I'm going to speed up a little. I want to finish this. Okay. So now we're going to derive the expression for Cv. Cv is the molar specific heat at constant volume. Okay? And Cv is defined like so. 1 over N internal derivative of internal energy with respect to temperature. We already know how to calculate the internal energy of the system of a gas. Number of gas molecules. Each degree of freedom is contributing 1/2 kT. And F is the number of degrees of freedom of the gas molecule. Okay. E is the number of gas molecules times F over 2 kT. Okay. And N times K is, so N, the number of gas molecules, is equal to the number of moles you have times Avogadro's number times K. And Avogadro's number times K is R. So this is equal to N times R. So this is equal to F by 2 N times RT. So Cv is 1 over N dE by dt equal to 1 over N d by dt of N F over 2 RT. D by dt of this, it kills that. The N cancels. Oh. N cancels, that gets killed. So Cv is F by 2R. Cv for an ideal gas is F by 2R. Okay. A monoatomic gas. What's a monoatomic gas? What is a monoatomic gas? Single atom. Which one is a monoatomic gas?
Hydrogen.
Hydrogen is a diatomic gas. All those noble gases, the last column, those are all monoatomic gases. Helium, neon, argon. That's why they're called noble. They don't mix with the riffraff. Okay? So, all those are monoatomic gases. The specific heat at constant volume is 3 monoatomic gases have 3 degrees of freedom. Okay, it's 3/2 R. So here's a very fun thing. Okay, so here's a monoatomic gas, it has only 3 degrees of freedom. A diatomic gas can have 5 degrees of freedom, 3 translational and 2 rotational. Okay, and a more complex molecule can have more degrees of freedom. Okay, okay. So CV is F by 2 times R. What is F? The number of degrees of freedom. So this is the graph for hydrogen. Okay, where does it say? Well, anyway, it's for hydrogen gas. Okay, H2 is a diatomic gas, okay. And you can find hydrogen molecules. Can you find them in the Earth's atmosphere? No. Where can you find them? In the sun's atmosphere. Okay. In Saturn, you can find them in Saturn, Jupiter, and all that. All right, so you're taking a hydrogen gas, and you're finding CV. CV, where is it? Where does it come? It's the delta T. If you have n moles of the gas and you're trying to heat, if you have 1 mole of gas and you raise the temperature by 1 degree Kelvin, that's how much heat you need. All right, when you're at low temperatures, CV is 3/2 R, meaning the degree of freedom is 3. For the same gas at a higher temperature, F is 5. So at these low temperatures, it has only translational degrees of freedom. The rotational degrees of freedom are not in play. What does that mean?
Not spinning.
Yeah, it takes too much energy to spin. I can't buy a Lamborghini. Okay, that's what that means. At an even higher temperature, the number of degrees of freedom was 7/2. What happened now? The vibrational degrees of freedom came into play. Now you can afford the vibrational degrees of freedom. Okay? So the amount of heat needed to raise the temperature of the gas by 1 degree changes. The richer you are, the more your monthly expense. Okay? Yeah, the richer your lifestyle, let's say, the more you want. So that's the more precise statement. Okay. All right. So the higher the degrees of freedom, the more energy it takes to raise your temperature. Okay. The specific heat increases.